Hello, everyone. My name is Chen Chen. I'm an assistant professor at the Center for Research in Computer Vision at the University of Central Florida. So in this presentation, I will talk about self-supervised deep learning for privacy-preserving video analytics. So video analytics as a service enables a wide range of real-world applications. For example, video surveillance, smart shopping system like Amazon Go, and elderly person monitoring system. However, these videos contain rich information, so there is a high risk of privacy leakage. For example, the gender of a person, the skin color, clothing, their individual's daily routine, and their home locations, and etc. So there's a pressing need to develop privacy-preserving methods for video analytics. So in the next, I will talk about our recent work that focus on video action recognition, and we develop a self-supervised method to achieve privacy-preserving action recognition. So this work is accepted at a CVPR 2022, and this is a joint work with PhD student Ishan Dave and my colleague, Dr. Mubarak Shah. So this slide, I show some examples that was took from the Toyota Smart Home dataset, which is for daily activity recognition. So as you can see here, these video footage can reveal a lot of privacy information, right? Like the gender of the person, their home setup, etc. There are several existing approaches that can be used to remove those privacy information from videos. So the simplest way is to reduce the resolution of the video. So we can do downsampling of each frame in the videos. So, so in this case, the privacy attribute can be maybe largely removed, right? Because we cannot observe the person, the appearance very clearly. And it does not require the privacy annotation, right? What is the privacy attribute within this video? But the downside is that it will degrade the action recognition performance a lot, because a lot of information are lost because of the reduced video resolution. The second approach is we can using some of the existing object detectors trying to detect like person or maybe some of the privacy related object from the scene. So in this case, the privacy attributes can be removed, and but obviously the action recognition performance will drop a lot. As you can see here, right? So the person in this frame has been entirely removed. So we can also, tell, what is the action is happening in this video. And another downside is that it requires the privacy annotation, right? To annotate these different privacy attributes. And recently there's a supervised adversary training approach to achieve privacy preserving for action recognition. So it is able to remove the privacy attribute by learning a normalization function, but at the same time, it is able to maintain the action recognition performance. So one limitation is that it is a supervised approach. It requires the privacy annotation. We propose a self-supervised framework, which does not require privacy annotation, and it is able to remove the privacy attribute and at the same time maintain the action recognition performance. And our approach consists of three components. So one is the anonymization function, and second is the action recognition branch, which is the utility task we know as FT. And the third is the self-supervised privacy removal branch. So we call it budget branch. So we can control like how much privacy information want to remove. And the goal is to learn a normalization function, FA, with the help of these accelerated utility and budget branches. And this slide shows the overall architecture of our proposed framework. So for input video, you will go to network. So this is a network used to learn an anonymization function, trying to remove the privacy information from the video. And then we'll have two branches. One branch is for action recognition, which is our utility task. And the other branch is the self-supervised privacy removal branch. I will talk about these individual components in detail in the following. So for this action recognition branch, we will leverage the action label during the training. So we'll just consider this a normal action recognition task and train the network on this kind of action recognition branch using the cross entropy loss. But for the self-supervised privacy removing branch, we are using the idea of contrastive learning. So basically, this is the framework of this self-supervised learning. So for a video XI here, it will go through a temporal frame sampler. So basically, we want to randomly select 2 frames. Okay, so each of the frame will go through this 2D CNN backbone network to extract some of the features to result a representation in the feature space. So let's call it ZI and the ZI prime. So these are the feature representation of these 2 frames. So for another video, XJ, which is a different video, we go through the same process and we generate 2 feature vectors, ZJ and the ZJ prime. Okay. So the contrastive learning idea is that in this feature space, we want to pull these features of the 2 frame coming from the same video close to each other. Okay, so we want the ZI and the ZI prime to be as close as possible in the feature space because they come from the same video. So in other words, they should share a lot of semantic similarity. So we want them, to be very close in the feature space. In contrast, for these feature vectors of the frame coming from 2 different videos, we want to push them further away because most likely they have different semantic information because they come from 2 different videos. So we want to push the ZI, ZJ further away or ZI, ZJ prime further away. Okay, so that's the contrast learning, and we'll minimize these contrast loss to learn a very good feature representation. So because we are not using any of the label information, so this is called self-supervised learning. Since we have several components of the network, here this slide shows the setup for the network initialization. So for this anonymization function FA, so we use an encoder-decoder based network. For example, the UNet architecture. So we have the encoder and the decoder. So basically, this will learn a normalization function to trying to modify the input video to remove some of the privacy information. For initialization, we're just using the identity function, right, to have an identity mapping. For the action recognition branch, we're using a 3D CNN model, which is able to extract spatial and temporal information for action recognition. And we're using some of the pre-trained model on some existing data set. So for the privacy removal branch, which is here, we're using a 2D CNN model pre-trained with the contrastive self-supervised loss, which we discussed in the previous slides. So to optimize the network, right, we want to learn a very good anonymized function to remove the privacy information from the video. And for this optimization process, in the first step, we are going to freeze the network of these self-supervised contrast loss branch, okay? And and we change the anonymized output such that it will minimize the action recognition loss to maintain the utility performance. Okay, so we also freeze the network of the action recognition branch, and we want to minimize the action recognition loss because this is our utility task. Okay, and also we want to maximize the contrastive loss in the privacy branch. Okay, so we free the weights of the FV branch, and we want to maximize the contrastive loss. So why do we want to maximize the contrastive loss? So if you recall, right, so when we initialize these contrast learning branch for the privacy removal, we use the self-supervised training loss, right? So this is the framework for the self-supervised learning, and we minimize the contrast loss such that the features from the same of the frame coming from the same video will be very close to each other, right? So they should because they share very similar semantic information. Now, here we are keeping the weights of FB freeze, right? So we want to maximize the contrastive loss, right? Which we were doing the reverse, before we minimize this contrastive loss. Now we freeze the weights and maximize the contrastive loss. So in this case, it will change, force the network to change the input to FB in such a way that it will decrease the agreement between frame of the same video. Okay, so that means the output come from generate out of the anomalous function here, will try to decrease the agreement between the frames of the same video. So we know that frames of the same video share a lot of semantic information, and minimize the agreement between them will result in destroying most of the semantic information of the input video. Okay, so these semantic information may contain those sensitive privacy information, right? Most related to appearance, etc. In the second step, we'll freeze the weights of FA, which is the anonymized function for learning the anonymizing function, right? Which is, we did in the step 1. In the step 2, we freeze the weights, and now we are trying to optimize the weights for these 2 branches. One is the utility branch, and the other is the self-supervised privacy removing branch to prevent some of the trivial solution. And we both minimize the loss for the action recognition as well as the contrastive loss. And this is a 2-step iterative optimization process. For experiment, we using the protocol by evaluating the anonymizing model on action and privacy classification. So the performance of action recognition should be retained, and the privacy classification should be degraded, right? So we're using some of the privacy classification method and trying to classify those privacy attributes. Ideally, we want the accuracy of privacy classification to be very low so that it won't reveal the attribute information. So for the prior protocols for evaluation, it was using action recognition dataset like UCF 101, HMDB. And we'll also consider human privacy attribute like face, gender, skin color. And for our experiment, we also consider new protocols for evaluation. That is, we also consider non-human privacy features, for example, the scene and the object. And we'll also have a collector data set, which is 24 times bigger than the prior protocol for more reliable evaluation. So this is the result we evaluate on UCF 101 and HMDB that is focused on the known classes of action privacy. So as you can see from this figure, right? So the vertical is the action recognition accuracy. So we want to have a high action recognition performance because that's our utility task. And the horizontal is the privacy classification accuracy. So we want the lower, the better. In this case, a lower accuracy means the privacy classifier cannot detect those privacy attribute very accurately. So based on the result, our approach, which is this red star, has a very close performance as compared to the state-of-the-art supervised approach, which is the blue square here. And similar performance can be observed for this HMDB data set as well. So we also evaluate on non-human related privacy attribute, like related to object, and also some attribute related to scenes. As based on the result, it is obvious our approach is very competitive with the supervised method. We also did the evaluation on novel action privacy attribute, which means some of the action privacy attributes are unknown during the training. So this is the result. So based on the plots here, our method has a little bit higher performance than the supervised approach, but the privacy accuracy is much lower than the supervised approach here. So our method is able to generalize well on the novel privacy attributes. So this slide shows how some of the qualitative inspection, during the training process. So this is the first row is the raw video frames, and the rest of the rows indicating how the frames evolve during the different training epochs, right? So up to the 30th epochs, as you can see that the frames, a lot of information are kind of private related information are kind of removed because we are learning this normalization function to change the appearance of the frame. And here's another example. And we also show some qualitative comparison of different methods with the input video, this bench press. And this is the obfuscation method, right? Just using a box to kind of mask out some of the regions. Let me play it again. And this is the method of using blurring of some of the person region. And this is the supervised approach. And the last one is our proposed method. And here's another example. As you can see here, we are able to remove some of the privacy attribute or information related to human and also the object in the scene. So in conclusion, we have developed a self-supervised privacy preserving action recognition framework. And our approach is able to achieve competitive action privacy trade-off to the supervised method. And for novel action privacy attribute, our method generalized better than supervised method. And the code is available so on GitHub. So you're welcome to try it out and see if the works on your own application or data set. So for future work, we also plan to incorporate the proposed framework into the federal learning paradigm. Right, so we know federal learning is a decentralized training approach that provides certain level of privacy, data privacy preserving, because we are not sharing the data to the cloud. But there are methods that can leverage the gradient or the model weights to reconstruct the original data, right? The gradient inversion approach. So if we are able to apply this, our proposed video anomaly method on the client side, right? We can first go through our approach, trying to anomalize our video, and then using that anomalized video to do the model training and sending the model weights to the server. So if there's attacker using the model weights or gradient, trying to reconstruct the data from the client side, the reconstruct data will be just those, videos, like doesn't contain the original information. So I think that provides an extra protection in terms of, privacy or data leakage. Okay. All right. That's it for the presentation, and thank you for your time and attention.